So to continue our topic of conversation about forces, I want to talk about the four fundamental forces and then hone in on one of them in particular. So we have four fundamental forces. You'll hear them called the fundamental forces of nature. Every force that you experience can be traced back to one of these four forces. And the first one here I'm going to talk about is the electromagnetic force. So it is the electromagnetic force. And this primarily describes forces between, or the force between charged particles. Between charged particles. And you may say, now this sounds like, the name sounds like two different forces. It sounds like electricity and magnets. And for a long time, they were, in fact, described as two separate forces. But then eventually they realized that the electromagnetic force and the electric force and the magnetic force were actually just two components of the same force. They're caused by the same thing. So that's the electromagnetic force. Then we have the weak nuclear force. A weak nuclear force, or you'll hear it just called the weak force. And this force is responsible for particle decay. Particle decay. So one particle may be losing some energy and literally a subatomic particle decaying into separate particles, separate and different particles. And hopefully in later videos we'll get to all of these that we're not talking about in this video in more detail. And number 3, we have the strong nuclear force, or again, just the strong force. And this force is responsible for binding particles together. Specifically, you could say it binds quarks together to make up particles like protons and neutrons. And then again, if you've ever kind of wondered, you probably know that the nucleus of an atom consists of protons and neutrons. And you might have wondered at some point, okay, the protons are positively charged, yet they're all stuck together. Why is that? And that's due to this strong nuclear force. And again, hopefully we'll be able to talk about that in a later video. And then finally, the last fundamental force that we're going to talk about in this video is gravity. And I think we have maybe an intuitive understanding of what gravity is. That's the force responsible for holding us on the ground and we don't all float away. And all of these forces, you may have heard of the theory of everything, and it's kind of this endeavor to get one theory that unites all of these forces. There's several movies made about this. The movie called The Theory of Everything and Interstellar, they mention this about unifying these forces. But we want to focus here on the force of gravity. Now, one important distinction to make before we get to start this is the difference between the force of gravity and the acceleration due to gravity. I'll use a different color here. So the acceleration due to gravity is 9.81 meters per second squared. It's kind of tempting to, when you're just talking quickly about this, to call that the force of gravity, but that's not the force. Remember, by Newton's second law, we have the force equals an object's mass. The force on an object equals the object's mass times its acceleration. So this acceleration due to gravity is going to be part of the force due to gravity, but it isn't in and of itself the force due to gravity. So let's look at exactly what the force due to gravity is. So the force that gravity exerts on a body is called weight. So weight is the force gravity asserts on a body. Now, we're going to use Newton's second law to get an equation for this force of gravity, or this weight. So if we take Newton's second, F equals ma, the most familiar form, and we say, all right, well, this force due to gravity, that's called weight. So we have a weight force. Now, the mass here, force on an object, it's still going to have, a mass. We're not changing mass just because we're talking about a different force. And this acceleration here, The acceleration due to gravity, well, we said up here was 9.81 meters per second squared, and the most common term, the most common notation you'll see for that is g. So this right here, W equals mg, this is the gravitational force, or you'll see this called weight. Oops, weight. So when you hear people talking about the force of gravity, you shouldn't immediately think 9.81, that's the acceleration due to gravity, but you should think the acceleration due to gravity times an object's mass. That's its weight. Now, we talked a little bit back in the acceleration videos that we kind of have a different sense of acceleration before we start studying it in physics, and it was kind of weird that you could be going 100 miles an hour and have no acceleration. There's something very similar going on here that we may have to rewire our brains a little bit, and that's the difference between mass and weight. Weight is this force due to gravity. Mass is intrinsic to an object. Your mass doesn't change whether you're on the moon, whether you're on Mars, whether you're in space, whether you're on Earth, but your weight does, because this acceleration due to gravity here on Earth is not the same as it would be on other planets. So it's always good to make this note that weight can change depending on location. Weight can change depending on location, but mass is a constant. It's a constant. Now we'll talk about some very special cases. Maybe you've heard of relativity and an object's mass changing. That's a different topic for this discussion of the force of gravity and this weight force. Mass is not changing. If I go to the moon, like I said earlier, my mass is still the same as it is now. So let's say somebody weighs 65 kilograms, just as a quick, easy example. So we have someone's mass is 65 kilograms. That's a unit of mass. And we want to know how much they weigh. What is their actual weight in newtons? Well, if they're standing on Earth, then we know the acceleration due to gravity is this 9.81 meters per second squared. That's the magnitude of the acceleration due to gravity. And if we want to find their weight, we just multiply the two. It's m times g, 9.81. And when we do that, it comes out to about 640 newtons. This is a unit of force. Newtons is the SI, the standard unit of force. Now, kilograms is mass, but if you're using the English system, we will say you will weigh someone in pounds, and that actually is correct. Pounds is actually a unit of force, so we can make a note that pounds is a unit of force. It's not what we're going to be normally seeing. We're going to be working with the Newton more than anything, but pounds is actually a correct unit of force, or a unit to measure weight with. Kilograms is a measurement of mass, and it's very important to always make the distinction between those two. Now, like I said in the last video, it's always good to kind of say, okay, this is all great, and to kind of find a situation that seems to not align with this, and then to look into it and figure out how it in fact does align with this rule and this weight and what we said about these forces. And so one thing that might come to mind is astronauts in space. Are astronauts in fact weightless? And so that's kind of a question. Are astronauts actually weightless? So maybe up in the space station, you have the astronauts in the space station orbiting around, and you may have seen videos and obviously heard that they just kind of float, right? Well, if they're floating, then it seems like they would have no weight. They're just weightless and floating around. But in fact, the acceleration of gravity, so we'll say maybe g in orbit on the space station, so maybe g orbit, is roughly 89% of the gravity on Earth. So they shouldn't be weightless. They should feel a little bit lighter, but it kind of seems like they shouldn't be weightless. And this is kind of an odd thing. This seems to fly in the face of, what we just said. They shouldn't, and what it seems like is happening. They're floating, but they really shouldn't be, right? And so if we take a deeper look at what's actually happening, so if this is the planet, and let's say they're in orbit around the planet. So they're orbiting around the planet in the International Space Station, and they're moving in uniform circular motion. They're going in a circle around the Earth. So why is it that they're floating? They do, in fact, have a gravitational acceleration, and then their mass, like we said, is constant. So they should have a pretty substantial weight. That's just slightly less than their weight on Earth. Why are they floating? Well, if we think about the spaceship here, so we'll draw a very crude spaceship. Nope, not that crude. Going around the planet in a circle, right? And then we have people on this spaceship. Well, the people on the spaceship are moving at the same speed and direction as the spaceship itself. And that kind of makes sense. It's what we'd expect. Well, remember, in uniform circular motion, there is an acceleration vector there. There's an acceleration vector, and this isn't the gravitational acceleration. If they're moving in a circle, we know that they have an acceleration vector toward the center of their movement, in this case, the center of Earth. Now, if the astronauts and the spaceship are moving around with the same acceleration vector, and they're always the acceleration is always pointing toward Earth, you could kind of think of them as falling, in quotes, toward the surface of the Earth. So as the spaceship is moving around, it's, quote, falling towards Earth at the same rate as the astronauts inside. And so you feel as though you're weightless for the exact same reasons that you get a little bit of a weightless feeling when an elevator starts to accelerate downward. If you were standing in an elevator, so maybe if we have an elevator right here, and there's somebody standing in the elevator, if this elevator starts to accelerate downward, you feel as though you're weightless. You start to feel lighter. Well, if the elevator was in free fall, right? If the elevator was in free fall, you would feel as though you were floating in the elevator because you would be falling at the same rate as the elevator. And that's what's happening in the space station. They're not actually weightless, right? They still have a weight, and it's roughly their mass times 0.89 times the acceleration of gravity on the Earth's surface. And so what would be more accurate to call this is apparent weightlessness. Apparent weightlessness. It feels as though they're weightless for the exact same reason that it feels like you get lighter when an elevator starts accelerating downwards. They still have weight, right? It's just that they're moving at the same speed and direction as the space station in a circle towards the Earth's surface. So this is called apparent weightlessness, and it does not violate anything that we've talked about.